Today on Crowded Garage, we're going to... Hey, it looks like my voice isn't matching my mouth. Do we have anything to fix that? Bop, bop, bop. La, 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 la.
Oh, you want a clapperboard? It's a device used in film making and video production to assist in synchronizing of picture and sound, and to designate and mark the various scenes and takes as they are filmed and audio recorded.
Oh, okay. How about this? The only real reason I need to sync video and audio is because I use this Zoom recorder instead of the camera's audio when shooting video. The circuit is actually pretty simple. Using a 9-volt battery, we're going to push a button to turn on some LEDs and make a beep noise so when we start filming, we can sync the light with the sound during editing. We first need to determine how to safely light 3 LEDs for a maximum brightness without letting the smoke out. Generally, the maximum current of an LED is 20 milliamps, but we'll try and operate a little under that. In a test setup using a 9-volt battery and 1 LED, and knowing that we want to limit the current to 20 milliamps, we can calculate the current limiting resistor we need to protect the LEDs. 9 volts divided by 20 milliamps equals a resistor value of 450 ohms. We'll use a standard 470 ohm resistor. And if we calculate for current for said resistor, 9 volts divided by 470 equals 19 milliamps. So, anode. Power. 470. And then we'll do this one here. If we connect the test circuit, the LED does light, but if we check the current, it's less than what we had calculated. To determine why, we'll confirm the 9-volt battery voltage being 9.2 volts, and then measure the voltage drop of the resistor and LED. We can see that the two values will add up to the battery voltage. The voltage at the LED and the associated current is the forward bias of the device in order to turn it on. We need to take this bias into account when calculating for the current limiting resistor. To do so, the bias voltage is subtracted from the 9-volt battery. 9.2 volts minus the 2.8 bias voltage divided by 20 milliamps equals 320 ohms. We'll use a 330 ohm resistor. Replacing the 470 ohm resistor with a 330 ohm resistor and rechecking the circuit current, we see that we are much closer to the calculated value. For the clapperboard, there are 3 LEDs in series, and we'll have to take all 3 bias voltages into account to calculate the current limiting resistor correctly. 9.2 volts minus 3 times the bias voltage divided by 20 milliamps equals 30 ohms. I don't have a 30 ohm resistor, but I do have a 47 ohm. I'll use that instead. To confirm, 9.2 volts minus 3 times the bias voltage divided by 47 ohms equals 15.4 milliamps. The test shows a little less, but I summed that up to relentless testing and depleting the 9-volt battery a little. Okay, let's start building. I have a project box, 3 white LEDs, the piezo buzzer, 47 ohm resistor, 9-volt battery and connector, and a momentary, normally open switch. Connecting the components will be as shown in the schematic. I'll mark out where the LEDs and switch are going to be located on the project box. Using some masking tape, a measuring stick, and a crayon to make short work of that. Pull out the drill and drill the holes, and we can install the LEDs. using a little hot glue to hold them in place. I'll mount the switch as well. I did a test to make sure that the buzzer could be heard with the case sealed, because what's the point of the visual if you can't hear the noise? I'll mark and drill another hole, hot glue the buzzer in place so that its opening is aligned with the freshly drilled hole. I put a little heat shrink on the positive lead of the 9-volt battery connector and then solder the lead to the 47 ohm resistor and the positive lead of the buzzer. Next is to solder the other side of the resistor to the first LED's anode and heat shrink the whole works together. If you are using used LEDs, you can determine which lead is the anode and which is the cathode by looking for a flat spot on the side of the LED body. The flat spot indicates the cathode. The cathode of the first LED is soldered to the anode of the second LED, and the second to the third LED. The cathode of the third LED is soldered to the negative lead of the piezo buzzer, add a little heat shrink, and then solder to one terminal of the switch. The negative lead of the 9-volt battery gets some heat shrink and is then soldered to the other terminal of the switch. And again, a little test. And syncing video and audio is going to get a whole lot easier. Add a little foam to hold the battery in place. And the back goes on, close it up, and we're done.